Okay, so last week we stated theorem 10.2. So this is the main theorem of the section, one of the main theorem of the paper, in fact. The first step in the localization strategy. And we started to prove it, but before continuing the proof, in fact, I have to relax a bit by preparing the course today. I realized that we can relax some statement, so we can prove something a bit more general. And in fact, we need. So in fact, we don't need. I guess we don't need this assumption. Okay. So you have SK. So let me recall briefly the statement. So you consider a spherical fusion category. You consider a self-dual simple object such that when you make the tensor square of this object, every simple object appears with multiplicity at most 1. So we need a self-dual object with this multiplicity 1 property. And then every component, the index of every component in this square make this set SK. So SK is a set of index for every simple object, which is in the component of X SK tensor square. Okay. Then we want also every component to be self-dual. So we assume that. Okay. And then, so we have this big set SK, and we consider a subset. And in fact, last week I said we need also to have that. But in fact, this is not necessary. The proof we will explain now, generalize a little bit the proof which is written in the paper, and in fact, I already updated it. I already did the update. Okay, and then so we have here we need to consider so I like that. So let I in SK, let BC in SK. Okay. And the rest is the same. Okay. And so now we will prove this. So we will prove that we can get this subsystem, which is very convenient because it's the subsystem of the full system of a triangular prism equation. And we will show later that the triangular prism equation is equivalent to the Pentagon equation up to a change of basis. So you have here a local subsystem of the Pentagon equation, and very useful because you can make it, for some small example, you can make this subsystem small enough to be solvable. Okay. So what else I want to modify? So here, in fact, so here, in fact, this is for all for all A, B, C in SK. You don't need to be in the subset. Here it's for all A, B in SK also. What else? And you can remark that. So remark also. Remark. So by this equation, see this equation ABC. The order in which ABC is written does not matter, because here it's a product of numbers. So you can permute everything, which will be the same thing. So we can write it as follow: for all permutation of ABC, X what is it? A, B, C equal XABC. So we will use that also. Okay. So in fact, here we are considering variable, but here, if you when you have ABC inside, independently of the order in which it is, you have only one variable, XABC equal XACB equal XBCA, etc. So it's only one variable. Same for here, only one variable, etc., etc. Okay, so okay, so the proof. So let me reread briefly what I wrote, what I started to write last week. So we consider three elements in the subset SK prime. And we will consider two triangular prisms labeled with this index. We will develop, so I will explain. I will write the TP with the label. We will develop it according to the simplified TP. And so the objects are self-dual and multiplicity at most 1. And the multiplicity in the TP are at most 1. So we can label only with bullet. We don't need to write a label for the TP. But we will see that for some equation, okay, I have to fix now that also. For equation 6 and 7. Because in fact now they will have also something in equation 6. Equation 6, 7. Okay. So we will see when we will develop the TP, the triangular prism, some multiplicity greater than 1 can appear. So, but we will see. You will see how we will handle that. Anyway, so so any object we consider appear in the component of xk tensor xk with multiplicity 1. So 1 is odd. So by the theorem proving one conjecture in the odd case, the second from Yunxiang indicator is 1, which means, as we explained before, that we don't need to orientate the edge. Okay. So okay. So now let me develop. Let me write the TP and the development. So the TP is as follows. So first, for this one, ABC and K everywhere. So you see how convenient is this graphical representation. Because you see how, so you put K everywhere, except in the middle, you have ABC. So it's quite natural to do that when you have such a graphical representation. You have a graphical representation. So in general, you have a different label everywhere, but we want to minimize the number of equations. We want to find a local subsystem as small as possible. So it's convenient to, we want it as small as possible, but we want it also non-trivial. So it's efficient to put as much as possible the same label, but not too much, because if you put it too much, then you get a trivial equation. So the variation is here. But this will be small enough, non-trivial and small enough to get an interesting local subsystem. So the development, so this will be equation 6. The development of that will be called equation 6. So sum for beta 0 in B0. So here you have already something which may not be of multiplicity 1. So as I said, now ABC, so I remove the assumption that on SK prime. So that's the previous assumption on SK prime was that the multiplicity among ABC should be 1, which means n ABC should be less than or equal to 1. So we remove that. We don't need that. Because we can, if it is of multiplicity greater than 1, we can put the basis, and we will see that we will be able to group together this as a unique variable. In fact, this is the same idea we did for the equation 7, but yeah, I realized that we can do that for equation 6 as well. Okay. So 1, 2, sum K di 1, 2, 3. Okay. Now, so don't worry, it will be very fast. And now you have beta 0 prime, beta 0, and you can put dot everywhere else. Ta, 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 ta. Okay. So the only multiplicity issue is there. But as I said, we will put all that as a single variable. Then, okay, let me change it. Maybe. So you have ABC, ABC, and K everywhere. ABC, K everywhere. I, K, K. Okay. Almost done. ABC. Okay. So this is the development of the first. So now what about the other one? So this, in fact, we will reformulate this into this. So this XABC, in fact, will represent this. So the variable here are not necessarily F symbol. Where is it? Here. This is not a F symbol, this is a sum of a product of F symbol. The sum of a product of a tetrahedron. But the Y will be F symbol. But in fact, the big advantage here is you want to solve a system. You can make a change of variable, and you can group together F symbol into a single variable, and then you solve according to that. And if there is no solution for that, then there will be no solution in general. And if there is solution, then you you can continue, or you can try to find the F symbol according to the solution for that, etc. So this is convenient, this is efficient to do that. So the second is this one. So let me write this second equation. So and so now you have K, so you have A and B here, A, B, C. Otherwise it's K everywhere. K, and K. And the development of that will be what we call equation 7. And here, so the left-hand side, there is no multiplicity greater than 1, so you just need to put two tetrahedron like that. And here, so for I in SK, di some beta in bases. And then we have 3. 1, 2, 3. That. Okay, so let me put first what is not necessarily of multiplicity 1 here. So beta prime, beta here. Maybe I should write it in red here also too, because you have to be careful about that. Beta 0 and beta 0. Zero prime, beta 0. Okay. We put what is not bullet, and then we can put the bullet everywhere in the reference pattern. So remember, note that the bullets are not positioned the same way on the left-hand side and on the right-hand side. And so the object. So let me put A, B, C first, and then it will be only K, A, C, and B, C, B, C. It is K or B? B, C, A. And then you have K everywhere else. K, 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 here, 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 and here. Okay. Okay. So I draw it very quickly, but I guess I draw this thing enough time. I guess there is no confusion what it means. Okay. So now what about the variable? So in fact, see, this part look like this part. And in fact, we will be able to move from one to the other. And this will be the same variable as you see here, this and this. And the other are just tetrahedron, which correspond to this tetrahedron and this tetrahedron and this one. So it's just a question of moving properly the morphism. Okay, so let I in SK be C in SK prime and consider the following variable. For in two types of variables, consider the following two types of variable. So the first type, X, I, B, C, will be the sum for B times B, something like that. So we group together the sum of product of F symbol. So maybe I can copy and paste. So which one is this one? Let me check it is exactly that. Yeah. So I realize I made a mistake here. I said it would be K everywhere, but I forgot. You have also the I. Here it's I, it's not K, of course. Let me check I did not make the mistake here. No, it's okay. So otherwise, let me check it is the same. Yeah. So I guess I can copy and paste this one. This is exactly the variable we want to consider. We can paste it here. Maybe I can make it smaller. Okay. This one. Okay. And the other type of variable is YIB. And this one will be where I will copy something. B, I guess. Yeah, it will be this one. So of course, ABC plays the same role here. So. Okay. Okay. So at least for this, this one, this is already the variable y, YIB, YIA, YIC, etc. And this one also is already in the good form. But now we want to consider this one. We want to make this one as an XABC. So we need to move some morphism. And also the same for this one and this one, maybe. Some, yeah. So I explain what to do. So it remains to reformulate the equation 6 and 7 with either variable, so with this variable. So the right-hand side of equation 6 and 7 are already okay, as I said. We only need to consider the left-hand side. So we need to apply the A4 symmetry on the left-hand side to recover our variable x and y. So it remains to reformulate equation 6, 7 with above variable. The right-hand side is already okay, is already in the good shape, is already okay. We just need to deal with the left-hand side. We just need to deal with, so moving morphism, which is rotation eigenvalue. The rotation eigenvalue and A4 symmetry for their left-hand side. Okay. So let A in SK prime, then by sphericality. So now we will explain how to do. So by using the sphericality and lemma 8, 2, which correspond to, so sphericality is for A4 symmetry, and this is for rotation eigenvalue. Okay, so okay, so X ABC. Oh, okay. Okay. So X ABC is the sum for B in B. So here I equal B. I equal A. So we define X IBC, but we can take I equal A. So sum of that. No, let me copy and paste. Will be better. Yeah. Okay. And we want to replace I by A. A and A. Okay. So we have that. Now, what kind of transformation we want to apply? Okay. So here we will apply a 3D move. So now the face on the floor is this one, and we want this one to be on the floor. So let me put this face on the floor. quite bad. This face on the floor. Okay, plus rotation. What we get is the following. So it will be equal to. So after some move, so I explain the move in green. So let me write it in green then. 3D moves. So you get something like that. So sum for B in B. So I only for now I only explain the move for the first, and I will explain the move for the second. Next. So you have to. So after this move I explain in green, you get something like that. Oh yeah. So now I have to. Oh yeah. Beta here. Okay. B. B. A. C. K. 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 So this face on the floor is a KKK. The KKK face is on the floor. And we rotate a bit like that in order to have B on top like that. Okay. So you have to convince yourself that it is this good. So as I said, this is only a 3D move. So let me explain how to quickly see where we can put the morphism label. For example, here, A, we have two labels. We have this one and this one. So the label which is about A is always outside. You see? It never, it's outside and outside. So you have A here. So the B is outside. Outside, I mean, in front of, if you have A, in front, you have this one and this one. So this is okay, and you can do the same for example, for B. B, for example, B here, beta is already put. But for example, you have a label here for morphism inside the face A, B, K. So A, B, K is here, and the label is inside this face. So this is how you can position every label like that. For example, yeah, you can do it face by face. Yeah, object by vertex by vertex, and then you see in which face. And yet then you can easily, because it is really a 3D move, you can just reposition everything. Okay. Now, what about the second one? So the second one, we just, okay, so here, made a mistake. This one should be beta prime. This one is a dot. If I'm not mistaken. Oh, wait. So then I made a mistake in my notes. Let me check. So where is it? X. Yeah, it should be there. It does not matter. Beta prime. Wait. Beta prime. Okay. Wait there. All right. So I was okay. So keys, where is it? Now I'm confused. So let me check. The beta is there, so it is okay. Now it's okay. Okay, and then here we make just for the second one, we just make a move like that. So it will be much easier to do. So beta prime here, 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 and K, B, C, A. Okay. So this is just this rotation. So this goes there, this face goes there, this goes there, etc. And this goes there, etc. So it's just that. So this is okay. Oh, what? Oh, okay. I was not in the good page. It is there. Sorry. Okay, so I hope I did not make. Okay, so first step. Now we want to move some dot and some oh, I see. So let me write it. So where is it? This one. Okay. So now we want to move. So I will write what kind of move we want to do. So we want to do this move for the dot, this move, this double move, this move, this move, this move. And in fact, I just realized that so before I made the modification during the preparation of the course, there is a dot here. But I so I generalized when I said I remove the assumption for SK prime. But now I have to be careful about moving that require to change a bit the basis. This will require to apply some rotation, some row. But but it's okay. I guess it's not a problem because what we will get here will be how to say, another basis. So we will move that here, for example, but what we will get here will no more be beta, but it will be rho of beta, or I don't remember. So maybe we can say the beta 1 or beta 0. Yeah, we can say beta 0. But I have to modify that. I have to be careful. So replace b beta 0. Okay, so what is the point here? What is the cost of this move? So the cost of this move is rotation eigenvalue. And the rotation eigenvalue was lemma 8.2. Let me come back. Lemma 8.2. Oh, I see. And so I have another problem here with my recent modification, is that to apply lemma 8.2, we need to have, we need this to be, we need the multiplicity to be 1. So I need to be careful. So I cannot do that now. So I will just write here a note. So I will have to do that later. So be careful. So sorry about that. I just modified that today. I did not realize. So I will make the pause and I will explain what I want to do later. Sound was muted. So let me set. So let me restart from the pause. So I was there. So I said that my update was safe. I was there. The update was safe. Ça marche le son maintenant. The update was safe because instead of writing rotation eigenvalue, here we will just write natural transformation rho for beta. So here we will have rho inverse of beta, and here rho of beta. And that's work. That's work because, in fact, it's the same thing as changing the basis. So we will, this new basis will be called beta 0 and b0, and this is the same. We have exactly what we want. So as I said, this move corresponds to that, which is different from 1 only if k equal b. This double move corresponds to that, this double move to that, and this move to that. So there is a non-trivial rotational eigenvalue only if the trivial vertex has only the same object on each leg. Okay, and for this one and this one, we will use the natural transformation. So we have something. Okay. So here it is rho inverse of beta. Here it's rho of beta. And then here we have so there, and there. Okay. And for the object, so ABC, B, A, C, B, C, A. So I have to put a beta prime somewhere. Beta prime. Okay, and ABC. Okay, okay, okay. Oh, sorry. Orange. Okay, 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 and K. And so you just need, so now what you have 2 points. Here, everything, this is equal to 1 because you have this. So let me write it. This is equal to, the rotation eigenvalue is a 3 root of unity. But we have that. KB times omega 3 delta KC. So this is 1, 1, 1, 1. No problem. So this is 1. This part is equal to that. Which is 1, because the rotation eigenvalue is a 3 root of unity. Equal that equal 1. Okay. And for this part, so where is my prime? My prime disappear. Prime. For this part, in fact, you just change the basis. So it is equal to so here, just write beta 0 equal rho inverse of beta. Beta 0 prime equal rho of beta. And B 0 equal so rho inverse of B. And here it's an abuse of notation. We apply the natural transformation for every element of the set. So it's an abuse of notation here. But anyway. And finally, we only need to finish this part. We need to put this one in first and this one in second. And then you will get exactly that. Get exactly that. Magic. The magic opère. So you get exactly what you expected. So that's nice. In fact, the preparation of this course permit me to make an update, and I fill a gap during the course. So it's quite challenging, but it's okay. It is okay. In fact, I guess I see that you have to check but I guess there is no problem that these are really dual basis. But it should be okay. Okay, so we are done with that. And in fact, you see, so initially, the initial version, we have a dot everywhere. So we have an extra thing here, ABC. So it was working as well. But we see, so we were able to make an update beyond for something which is not a multiplicity one, and we were still able to handle. So maybe there is a hope for a generalization of such result beyond this. So we already remove this assumption, but maybe we can remove this assumption or this assumption. Anyway, that requires extra work. Okay, so we are done for the first equation. The left-hand side of the first equation. So for the left-hand side of the second equation, in fact, this is the same. In fact, it is much easier because we don't need to deal with something which is not of multiplicity 1 here. So more easily. So similarly, easier. So YAB, YAC equal. So you just write the definition of what is YI. So this one. So let me just copy and paste this. Now you have to replace I by A, I by A only. A and A. Okay. And now I will leave it as an exercise, but as I said, there is no difficulties. It's the same. So here, the move like that. I did not wrote. So the same. So exercise, you get something like that. So something we want. So maybe I can copy and paste also. So the left-hand side of the second should be that. Yeah. So you get that. It's too small. Okay. Nice. Okay, so we are done with this. Now we have to explain why we can make this, all this. So I guess this one is direct, you just have to write. This one is just a 3D move. This one is trivial because you have a tetrahedron, we have ABC here, so this corresponds to the multiplicity of the homospaciality 0, then the tetrahedron is 0. Then we have to explain that. And in fact, that is not explained in the paper. So during the preparation of this course, in fact, I prepare the explanation for this one, and I guess this one will be the same. And it is during the preparation of this explanation, I realized that I need to relax the assumption of S prime K. At least to relax that was very helpful to prove that. But maybe it can be proved directly without this generalization, but hopefully I am safe about that. But okay, so it remains to prove all the equality at the end of the theorem. So all this equality like that. So by this, I refer to that. So how many? 1, 1, 2, 3, 4, 5. And that is okay. So 5. 1, 2, 3, 4, 5. Okay. Okay, so XAKK is equal to that, so XABC. I will take this one here. This one. Copy. Paste. Here, its multiplicity one is KK. So this corresponds to I BC. So I equal A, K, BC, KK. So K and K, K, K. There is no K, 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 K. And I is A. And there is no multiplicity here because by assumption, the component of xk tensor xk are of multiplicity 1. So I can put that. Okay, but this is in fact exactly the shape of y, if I'm not mistaken. You see? So if you put a dot here, this shape is exactly this shape. So this is directly y y-ak times y-ak, so y-ak star. Okay. Then y-ab equal to, so I will copy this one. And I will be A. Now. And here, you just need to make a 3D move. And in fact, the 3D move will be enough. There is no need to deal with rotation eigenvalue. 3D move. So we want to put, so the face on the floor is KKB. We want KKA on the floor. So there are two KKA. Which one of the two, in fact, I guess it will be. put it on the floor, and then oh, that's strange. Anyway, you get exactly, in fact, the same. You get exactly the same, but with A and B. So there is nothing to deal with rotation eigenvalue. It's just like that. B, A. Okay, this is Y, B, A. Okay, so that's okay for that. Next, I want to explain this one. Where is it? This one, I will explain this one, and I will leave this one as an exercise. But in fact, the proof of this one is at least it's yeah, it's a little bit more complicated. It's a little bit tricky. So you have to be careful. Okay. So let me explain this. Now, let us prove that. Now, let us prove that we have that. In fact, what is the idea here? The idea is that we already have equation. So the equation are proved, in fact. So we prove the equation. So we have this equation. What, yeah, these two equations. So what remains is to prove that. But in fact, we can reuse this equation to prove that. And this is what we will do. But as I said, it will be a bit tricky, or at least maybe the proof can be simplified. So, okay. So clearly, x, I, B, C is different from 0 if and only if the dimension of the base B is different from 0, which is equivalent to NBCI different from 0. So clearly, why is it clear that IBC different from 0? So why I need that? Maybe I don't need. Why 1, 1? So I just need y 1, 1. I don't need YBC. So clearly, that. I hope, I guess I don't need that. Y 1, 1. Different from 0. Here there is no multiplicity, so it reduced to something like that. So is it clear it is different from 0? So let's assume that as an exercise. So exercise. So it is different from 0. Next. So we already know that y, we already show that YAB equal YBA. Okay. So now, what about Y1A? Y1A. It is this one with B equal 1. Okay. But when it is 1, in fact, it's the same thing as putting nothing. But let me, so in fact, here I just want to show that this is non-zero. Okay. So this is, so in fact, the proof of that is non-zero will be the same as the proof of that is non-zero. So let me show. In fact, if you write it as a monoidal tetrahedron, and you put just a dot as a label, in fact, so you have this, and this, and this, and now you have this one. So in fact, we will not draw it. And finally, this and this. So here, it's K and K. This is one-dimensional. This is a morphism from K to K. The home space from K to K is one-dimensional. So here you have a non-zero multiple constant of the co-evaluation map. And same here. So you get some constant, some constant, non-zero constant different from zero, and something like that. You replace, you do like that. And this is, and this one is not drawn, no more drawn because it's one. So you have tac, 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 tac. So you have this multiplicative constant of co-evaluation map here. You have a co-evaluation map here, which go like that and like that. And then you have like that. And by zigzag relation, this is equal by zigzag. This is nothing but that time a constant, non-zero constant. But this corresponds to the basis. This is the bilinear form on the basis. So we know that this is a so this is a dual. This element of the basis and this one are dual to each other. So this is non-zero. This is non-zero. So this is non-zero. Okay. So this, I guess there is a easier way to do that, but this is just to prove that this is non-zero. And I guess you can do the same thing for that. You can prove this is non-zero like that, but I guess there is a much easier way to do it anyway. Now you apply equation 5. So equation 5, the first one of the second, yeah, you apply this equation. 2b equals c equal 1. Okay, and you take a to be any element of sk. So you take here, you can consider, you can take sk prime equal sk, because there is no more restriction of sk prime is just a subset of sk. So you can take sk prime equal sk. And so you have this equation, you replace b and c by 1, and a is any element of sk. Okay. Apply this equation with b equals c equal 1 for all a in sk. So take sk prime equal sk, for example. Then b equals c equal 1. So you get ya1 square equal the sum like that of di yai xi 1 1. If I'm not mistaken. Right, b equals c, so equal 1, okay. A, it's okay. It is okay. So we have that. But this is non-zero, as this is non-zero. Okay. And remember, so this is non-zero if and only if. So wait, what is non-zero if and only? So I am confused. This is non-zero if and only if y equal 1, of course. And in fact, you don't need, because this is you consider this this morphism. Yeah. So this is non-zero if and only if, and you don't need, in fact, you don't even need to write as an exercise. This is immediate if and only if I equal 1. Okay. So the only tricky part is only to prove that this is non-zero. So this is non-zero if and only if I equal 1. I equal 1. So sorry about this confusion here. Just why? This corresponds to that, in fact. But I said it is trivial. It is non-zero if and only if this is so this is 0 if this equals 0. But if b equals c equal 1, there is no problem of multiplicity. Okay. B, C, yeah, you consider this part. So if, anyway, it's okay. It is okay. So this is non-zero if and only if, blah, blah, blah. So in this sum, you only need to consider I equal 1, because otherwise it will be 0. Because if I is different from 1, then you have to consider I don't remember, n11i. And this is trivial, so it should be trivial here. So you can fix I equal 1. So it is equal to d1 y 1a x 1 1 1. Okay, but y1a equal y1a1. So we showed that before, so we don't need to recall it here. So next here it's y1a is different from 0 because. Okay, and so as we explained before, this equal to this. So this the same, and this is non-zero. So we can simplify by one component here. So you get that then y1 equal x111. So it's equal to y11 if you like, because this is for all a in SK. So it's a constant. So this is very, very important. So this does not depend on a. It's a constant, y11. Okay? So constant. Okay. So finally, you apply equation 4 with a equal b equal c. We get something like that, x111. So equation 4 was x abc equals sum di, y ai, y ab, y ac, etc. But you put everything equal 1. So it's equal the sum of di, I in sk, ya1 cube. Okay. But 1a1 do not depend on I. This is just 1, 1, 1, which is that also. So y11 equal sum y in sk di y11 cube. You can simplify because it's non-zero. So y11 power minus 2 equals the sum of di I in sk. But this is, remember the definition of sk, this is the sum for I, for all I, of n k I di. So remember that an element in, so k was by assumption such that any element in the component of xk tensor sk is of multiplicity at most 1, and the one which is exactly 1 make this set. So this is okay, this is like that. But this is what? This is dk square by the dimension equation. So you get conclusion y11 equal dk inverse. And this is what we wanted to prove. So you see how it is. It was a bit tricky. So I really expect a shorter proof, but so we have to be careful about the choice of the element of the basis, because in the preliminary section we consider some basis where everything was orthonormal or something like that. In fact, you have to be careful. Yeah. Anyway, so according to what we do, according to what we did, we have no choice. So this F symbol is fixed. So we already fixed this F symbol. And in fact, all the F symbol so the initial statement to prove was 1. So all these F symbols are fixed like that. Dk inverse. Yeah, here. So if you put A equal 1, then this F symbol is known as dk inverse, independently of what is B. Okay, and so so I leave as an exercise the last one, and it will be enough for today. So this one will be exercise. Exercise. Prove that we have that. And that's all for this proof. And okay, so I guess it's time. It's just time. So we will see another. In fact, tomorrow we will take this, the equation proved in this theorem, and we will make some few transformation to get the system a little less general, but a little bit more appropriate for what we need. And then we will prove, in fact, we will prove another theorem saying that if you have two systems like that, which are quite similar, you can find an extra equation which can connect the two. And this is exactly the strategy we use to exclude one fusion ring. So I will explain that tomorrow, but we can stop here.